A straight hill has a length 400 meters with A at the top and B at the bottom, is inclined at 4 degrees to the horizontal. A straight road BC has length 750 meters. A car of mass 1250 kg has a speed of 5 meters per second at A when starting to move down the hill. While moving down the hill, the resistance to the motion of the car is 2000 Newton and the driving force is constant. Constant driving force means you could use equations of motion here, by the way. The speed of the car on reaching B is 8. Using work energy, find the driving force of the car. Okay, let's do that. So let's take a look at this part of the motion. We're going to use work energy principle. Work done by driving force plus loss in energy is equals to work done by resisting force plus gain in energy. Okay, so we need to find the driving force. Work done by driving force is the driving force times the distance covered, which is 400 plus loss in energy. As the car moves from A to B, the potential energy will drop by mgh. M is 1250, G is 10, and difference in height would be 400 cos 4 sine 4, sorry. Is equals to work done by resisting force. The resisting force is 2000 times distance 400 plus gain in energy. So the gain will be in kinetic energy, and the speed is was initially 5 at the top, now it's 8, so it's a gain in kinetic energy again. So half times 1250 times bigger speed squared minus smaller speed squared. Okay. Now you solve all of this and make FD the subject. And what should you get? This is 10 times 400 sine 4. Okay, it should come out to be 1188.9815, which rounds to 1190 newtons in three significant figures. Okay. On reaching B, the car moves along BC. The driving force is constant and twice that when the car was on the hill. So again, the driving force is constant. So if needed, you can use equations of motion here. And equations of motion work when acceleration is constant, which is when the driving force is constant. And the motion should be in straight line. So all those criterias work from B to C. So you could use equations of motion if required. Okay, so back to the question. So the driving force is now twice of the initial driving force. I'm going to do 2 times 1188.9815, which is what? Answer times 2. I'm getting 2377.6963. Okay. Uh, The resistance is still 2000. Find the acceleration of the car while it's moving from B to C. So we're going to use the formula forward force minus backward force is equals to MA. Forward force will be the driving force. The backward force would be the resistance. So forward force 2377.963 minus the force of resistance 2000 is equals to mass times acceleration, which gives us A equals 0.302. 0.302371 rounds to 0.302 meters per second square. Can find the power of the car's engine as the car reaches C. Okay, so to find the power at C, power is equals to driving force times velocity. So we know the driving force, that is this 2377.963. Now we need the velocity or the speed of the car at C, so that we can find the power of the car's engine at C. Now to find this C here, sorry, the V here, you could use equations of motion or you could use work energy principle. I think I'm going to use equations of motion. U is this value, which was what, which it was 8. U is 8, the speed at B. V is question mark, which is the speed at C. S is 750, and we just found the acceleration, that is 0.302. Okay. Again, equations of motion are only working because it's a straight line and because the acceleration is constant from B to C. And we know that because they've told us that the driving force is constant from B to C. That's why. Okay. Otherwise, you would have to use the work energy principle like this in part 3 again. Okay. So we need V. So V is equals to square root U square plus 2 AS. This comes out to be square root of 517. Now let's find power from here. So 2377.963 times square root of 517, which gives us the power of the car's engine at C, which comes out to be 54,069.255 or 256 watts, which can also be written as 54.1 kilowatts.